Hi and welcome to video 5 in our video series on forces and motion to do with differential equations, and today we're going to be talking about simple harmonic motion, as you can see there. And so in this video we'll introduce simple harmonic motion, do a couple of examples, and then we'll probably have a second video with a couple more examples. So let's have a look. Simple harmonic motion is movement under conditions where the acceleration of the object is always directed towards the center of motion and is proportional to the distance of the object from the center of motion. So this is a differential equation, but we're told that the acceleration, so d squared x dt squared, is equal to k times x. It's proportional to the actual displacement as stated here. So you've seen this before. In terms of, have you seen pendulums, have you seen masses on a spring, maybe you've been at a park and you've seen people on a swing. Obviously all these situations in real context involve some form of frictional force, wind resistance, usually pretty minor, but that will slow the motion down. Eventually the motion stops. But under a perpetual system, the swing, for example, would swing back and forth forever, and it would be following this differential equation that the motion would be described. So let's have a look. Here's our standard forms. The pendulum or that spring bouncing up and down are two fairly common forms, and they look a bit like this. So I've got the pendulum and the spring there and the functions that they follow. So a spring, and the assumption being with this spring that of course it's pulled down and therefore starting from that trough position, and then it bounces up. You can see it's steepest here, and therefore that's where it's got the fastest speed, the velocity, and then goes up the top. It's got zero velocity there, but that will be the maximum acceleration, which makes sense, and also matches that acceleration is proportional to the distance, and that's the furthest distance from the center of motion, and it just continues to do that. In actual fact, it is damped motion, and eventually it will go down to zero, but we're not too worried about that today. We make the assumption there is no other forces in place. Here's the pendulum, and it's got this same shape. It's just we're looking at it from a different angle, but the same shape applies here. It's pulled out to one edge and then released, and it follows that simple harmonic motion. We have a max displacement and a max acceleration occurring at the same time, whereas the maximum speed is in the center of motion. So let's have a look at the mathematics behind it. So we say that in a simple harmonic motion situation, and we're just talking about one dimension, so if I just go back up to this pendulum swinging here, obviously the spring is pretty obviously in one dimension. The pendulum, we sort of talk about the center of motion being there, and it comes out to there, and it comes out to there. There's obviously an up and down motion as well that we would deal with in another context, but in this situation we're looking at that horizontal motion for a pendulum. So horizontally, x is equal to a sine omega t plus alpha, and in this case we've got a is the amplitude, as you remember from our work with periodic functions. We've got that alpha is the phase shift, but remember the phase shift occurs when we factorize the b value out, which in this case is omega, and omega is related directly to the period as 2 pi over t, and so you've seen this as b, and you've seen that as minus c. They're the common places you've seen these ones, and this often we see as a in our function transformations for periodic functions. But now let's have a look at how we derive these formulas that come about due to simple harmonic motion. So over here I've got my displacement, and then x dot is my velocity, and hopefully you can see that my velocity is equal to a omega cos omega t plus alpha. That doesn't change on the inside. The sign goes to cos, it stays positive, and we get a factor of omega on the outside. And of course I can also determine from this x double dot, which will be a omega double dot, and then sine omega t plus alpha, and of course that will be negative because cos goes to negative sign. Now we can rewrite this slightly differently. It gives us negative omega, so that should be double dot, that should be squared, my apologies, negative omega squared times a sine omega t plus alpha, and that of course is negative omega squared times by x, because x is equal to that other thing we've got there. And so we get x double dot is equal to negative omega squared x, which is negative of omega, which is related to the period. That's our b value at 2 pi over t x. And we might be given some information, and you've seen it in circular motion already, how we might develop and determine what omega is. So there's our first relationship. The next relationship comes from a little bit of work regarding our x and x dot. So let's have a look at that. I'll just draw a line under here. So let's imagine that in the first instance we take x and we square it. So we get x squared, a squared, sine squared of this stuff in the middle. And then we get our second one and we take x dot squared. And that's equal to a squared, omega squared, cos squared of this stuff. And then of course we could add those together, but better yet we could treat this a little bit like when we're bringing together that circle function in parametric form. So I know here, I know where this is leading, I want to cancel out those sine squared, cos squared when I add them together to get 1. So what I'm going to do instead is I'm going to get my function 1, I'm going to write it down as x squared over a squared is equal to sine squared omega t plus alpha, and function 2, I'm going to write that down as x dot squared over a squared omega squared is equal to cos squared omega t plus alpha. And of course this leads to, and I've got an arrow here, preset, ready to go, it leads to 1 plus 2, which is x squared plus a squared plus x dot squared over a squared omega squared. And that is of course sine squared of some stuff plus cos squared of the same stuff, which is happy days because cos squared and sine squared, as long as it's the same thing, is equal to 1. So we get this whole thing is equal to 1. Now I'm going to multiply by a squared, omega squared at the same time, and that will give me omega squared x squared plus x dot squared is equal to, now this became 1, so now it's a squared omega squared. Do a bit of a subtraction, I'll get x dot squared equals a squared omega squared minus the squared x squared. Take out the common factor and take the square root. X dot squared equals, x dot is equal to the square root of omega squared a squared minus x squared. And I can write this down now as my final value, which is velocity is equal to omega times the square root of a squared minus x squared, which of course is where that arrow led, because that arrow goes straight to here. So we've got, and I can write that up here as well. So we get, we've got a capital A instead of a little a, so we'll make that change. We've got x dot, which is velocity, is equal to, that should be squared there, shouldn't it? Is equal to omega and then a squared minus x squared inside the square root, and that velocity squared is equal to that. Either of those relationships works, they're the same relationship, one with the square root, etc. So we've got our nice relationships now, they actually work out really well for us, but sometimes these three here are just as good. It really depends on the information we've got as to which one we might use. So let's look at one example. A particle moves in a straight line such that a, the acceleration, is equal to negative 4x. And mind you, this is why we tend to use this guy here, capital A instead of little a, because little a equals acceleration. So there's the reason. Particle moves in a straight line such that a equals negative 4x, x equals 3 when v equals that initially. Explain why this particle exhibits SHM. So the reason it exhibits SHM, the reason we can prove that, is that the whole premise of simple harmonic motion is that acceleration is proportional to the displacement, even if it's backwards. And so in this case, we get acceleration is equal to negative 4 times x, which equals negative 4 times x like that, where k equals -4, and therefore acceleration is proportional to x, and hence simple harmonic motion is satisfied. And you'll note here that not only that, k is equal to -4, but we know that it's negative omega squared is equal to -4, so omega is equal to 2. So that's important as well. Determine the period of motion, the amplitude of motion, and the displacement at time t. So in part B, we're being asked to determine 1, the period, which is 2 pi over omega, that's t, capital T. 2, the amplitude, which is our capital A from that relationship. And 3, x equals some function of t. So that's what it means by the displacement at time t. They're the 3 things we're being asked to find. The first one's hopefully fairly trivial. That's 2 pi over 2. And 2 pi over 2, of course, is equal to pi. So therefore, t is equal to pi. And it's a period, so it's pi time unit. And we don't have a time unit, so therefore we're not sure what the units are. So we'll leave it as that. 2, I want to find the amplitude. Now, the interesting thing here is that I know at x equals 3, velocity equals -6√3, and I know that velocity squared is equal to omega squared square root a squared minus x squared. Now this is an identity, so for all velocities they are equivalent to the displacements at that point, and omega and a are constants. But we have a specific situation, and so it must be true. We also know omega, so we get -6√3 squared equals 2 squared times the square root of a squared minus x squared, which in this case is 3 squared, and we can rearrange it. So -6√3 becomes a positive. 6 squared is 36, √3 squared is 3, 36 times 3 is 108. 108 is equal to 4 times by, oh, that shouldn't be the square root yet. I've got that formula wrong because it's squared. Be careful of that. That's just brackets. My apologies. Times by a squared minus 9. So 108 divided by 4 is 27, of course, is a squared minus 9. So we add the 9 on, we get 36 is a squared, and therefore a is equal to plus or minus 6. But as it's amplitude, it's asked for the amplitude, we give it in the positive form. So we say a is 6, and we don't know the units again, so we just need to be a bit careful of that. And then lastly, we're asked to find the displacement at time t. And this shouldn't be too tricky, given that we know a couple of things. We know, first of all, that displacement is equal to a. Now, we can use sine or we can use cos. And if we go back to here, it doesn't really matter where we started. We started with a sine here. But you'll notice here that when we go back to original models, well, we kind of pulled this out, which meant cos made more sense, and we kind of pulled this down, which means that cos makes more sense. So sometimes we start with cos as well, but the acceleration displacement model still links because cos derived twice goes to cos, just like sine derived twice goes to sine. So I'm actually going to use the cos model here, and it doesn't make a huge amount of difference which one I use, so I'll show you that. So let's use the cos, and inside we have omega t, and we'll use a plus alpha, and it's the plus alpha that makes the difference here. Without the plus alpha, this would be really important, but with the plus alpha, cos can be a sine curve, it's just the alpha changes. So we're going to use the plus alpha. Now I know a, I know omega, so I get x is equal to 6 cos 2t plus alpha. And notice here, if I made x -6, it would be inverted. So for that spring being pulled down, using a negative amplitude actually makes sense because I start from that lower point. But if I used a positive, it would just mean that alpha changes again. It's just a different phase shift, and it's all good. So going back to the question, I know that it says here initially x equals 3. So I'm going to use that. And that's another good reason to pick cos, because I know it's not initially 0. So at time equals 0, x equals 3. So I get 3 equals 6 cos 2t plus alpha, and that means that a half equals cos 2t plus alpha, which means that I get cos inverse of a half, which hopefully you'll remember is pi on 3. Cos inverse of a half. There's a few answers, but I just want the first and obvious phase shift if I can. So I get, oh, and of course t equals 0, doesn't it? So that means that cos inverse of a half just equals alpha. So I've got alpha there. I should change this to a 0 as well, shouldn't I? And so alpha equals pi on 3, and therefore x is equal to 6 cos 2t plus pi on 3. And there's my function x related to time. So I'm going to leave it there for this video. Hopefully that's helped. I've got a couple more examples, so if you want to jump on the next video, you can have a look. All the best.